a private meeting also. But the thing is, for the first day, what we will do, we will introduce the basic things, and it's actually very fit for a public meeting. So that way we can also maybe we can do something which will benefit others to learn some basic topics, basic research topics, and as well as start with our project.
What is this project?
Yeah, I'm coming to that. So the name of the project was too big to write, so I made a abbreviation, and let's see. Oh. Okay, so everything started with this. So this is the page where we applied for the project. It's an Indo-French project, and I didn't know about it. So Professor Shubir Ghosh came across this.
I was told that, see, I was a part of Indo-French Center collaboration long back, so it was going on with me, missing it, so they informed me that whether they wanted.
Then he started speaking with Shandip Das.
He's now the French partner. I was looking for the French partner, and he came into the picture.
So then I asked Eric and Reza, and then we actually could write a project. But the thing is, we had only 7 days to write this project, whereas ideally we should have maybe 2 months, 1 month, I don't know. But then, and I never knew how to write a project. Now, Professor Ghosh helped me a lot. So he briefed me, okay, these things are this, you have to write the budget separately. For some budget, you have to write in euros, some things you have to write in rupees. And these things, I mean, these are something you cannot know, and it's nowhere explained. So he gave all these details, and then Reza came up with a very good application of graph homomorphism, which incidentally Florent actually works on. His postdoc is on that right now, on graph database. So together, all these things made the project happen. And also, you see, even in this page, the deadline got extended. So the deadline is extended to May 7th. So we got 7 days more. Otherwise, I don't know. So, and finally we got the project. So I'll just walk you through the members. Okay, so these are the French members. The principal investigator is Reza Nasser from Paris, Detroit. How do you call it? Diderot. Okay, close approximation. And so, well, from the same university, Christina and Amile. I haven't met them, but they are Reza's colleagues, and they also work in this graph database. So probably you know them? No, not yet. So, and then Florent from Clermont-Ferrand. He was in Bordeaux. He was doing PhD at the same time when I was in Bordeaux. And we share one common supervisor, but not Eric. It's someone else, André Raspo. And then there is Julien and Theo. Theo is a present PhD student of Eric. And of course, there is Eric from Bordeaux University. And Julien, Theo, and me, we share one common advisor, that is Eric, again. And then I haven't met Dimitri yet. He's supposed to join, or he joined already? Okay, okay, right. And some of the affiliation changed in between. No, nothing changed here. Okay. In our case, some of Maharaj, where do I have to point this to? It's
actually, the computer is
I have to point it here. Okay.
It should work either way.
Okay. Yeah. So now the Indian members. So we have already introduced ourselves. I'm Sagnik. So I was in RKMVery here back then, and now I am in IIT Dharwad. And Shandip Das is in ISI Calcutta. Shubir Ghosh is in RKMVery. And then Joydeep is missing because he had a small matter of a PhD defense to give. So he went for that into Chennai. and IMSC. Dibbayan is here already. He's coming back like 2 days. He will be here for 2 days. He can attend the, yeah, because he has his PhD defense on 1st February. So, yeah, but it's in Chennai. He wants to get his degree also. Yeah.
Okay, good. At least he should have his degree. Okay.
So your classes are over, or? Oh, okay. Okay, good. And then there is Uma. Uma is not here. He's coming in a few minutes. And Harminder, you haven't seen him yet. He went to fight or something. He does a lot of kung fu kind of sports, so maybe he has a course, but he will join us soon. He has a talk. The last talk is his, today's last talk. And then there is Swati Prabhu Maharaj, who is here. And
the host here.
And the host. Well, you are also the host. You cannot, but he is the main person who has arranged all this. And right, right. And also one more thing, that this whole room, this is, as you can see, it's a new facility here. And as I told you, this is a new university. Well, not according to the timeline or registration paperwork, but it's kind of a startup university according to the courses, especially the computer science department. And this was a facility which Swati Maharaj had worked on obtaining a lot, and he had given a lot of time to get this whole facility. This was built under his supervision. So as you know, with my email, that the whole thing will be streamed live. So I'm right now on camera, and I hope I don't make stupid jokes. And well, and it will also be uploaded later on in the university website. And hopefully we will get one website of our own about this project, and we will also put the links there. So anyone can go there and check. Okay. So there are 2 external collaborators for now. That means in the original project we didn't mention them, but they are collaborating with us anyway. They're not part of the visiting program, but they will be collaborators. It's good to list them like Reza did for your French project. So that's Shomen Nondi and Bodhayon. We have already introduced them. So Bodhayon is in Czech Republic. So now your affiliation,
No.
you are unemployed now. Okay, that's great.
For 1 week.
Okay, because he told me that he is joining on 7th February.
In
And
IIT Dharwad.
I know.
So 1 week he's
So,
unemployed.
so 1 week you don't have affiliation, blank. Okay.
So you will be now affiliation with IIT Dharwad.
Yeah, it will be, but not today. Okay. So I have put some dots in 3 because we expect more collaborators soon. And let's see. Now about this, what is this project all? Okay. Now the name, your question. So the name was application of graph homomorphisms, and there is a similar project which Reza and Eric, they obtained in France. It's a French project. It was called homomorphism of sign graphs. So they made an abbreviation of it, which is called Hosigra, and they are maintaining a web page called Hosigra something. And if you search in Google by Hosigra, you'll get it. So I thought maybe we can do the same thing. So it was easy because once we wrote this, everyone liked the name. It means in my mother tongue and all the collaborators' mother tongue, right? Indian collaborators. We have the same mother tongue except for Maharaj, but he speaks that language very well. So it's agroho, which means inquisitiveness. So it's kind of a nice meaning also. Yeah, okay. So that's why agroho. And then the broad topic of our project is graph homomorphisms. but then there are different kinds of homomorphisms that we will study, not only the classical homomorphism of simple graphs or directed graphs, but there is mixed graph, colored mixed graphs, oriented graphs, so they are sub part of it, and then 2H colored graph. Then there is something called signed graphs, and that Eric will be speaking about. So today I will, so actually homomorphism of simple graphs is a much classical thing, and I will maybe start speak a little about it, and our project is after that, whatever is after that. So one of the big things is signed graphs, which Eric will be speaking about, and then another thing is a generalization is colored mixed graphs, which I will be speaking about in the beginning, so that you get the big picture first and then focus on each topic. And then there is oriented graphs. Swati Prabhu Maharaj will be speaking about it. He just did his PhD on this topic, so probably the best candidate to speak about it. And then there is a small extension of oriented graphs. Not much work has been done in this topic, but still worth mentioning. It's pushable homomorphism of oriented graphs, and Shandip Das has volunteered to, well, he didn't actually volunteer, I forced him to do that. And then there are applications. So the primary application that we mentioned in our project is query evaluation in graph database. So Floha will be speaking about that part today. And then there are 4 other topics which so there is some connection with homomorphism. It's loosely connected, let's say, but it's still in our project, and these are listed as auxiliary topics. So one is channel assignment problems that Shoumen Nandi will be speaking about. And 2 and 3, isomorphism of visibility graphs and chromatic art gallery problem, 2 very interesting problems, which are actually research area of Shubir Ghosh and Bodhayan. So Bodhayan will be speaking about that, both of them in the same topic, right? So I don't know if you actually mentioned this problem, but it will be something related on visibility graphs, right? Okay. And then Harmender will be speaking about cops and robbers. He knows judo, so he is cop or robber, depending on who wins. So
He works on cops and robots today, online version or?
that I don't know, because I don't work with him. So online or? No, I think he, yeah.
Graph searching problem.
Yeah. So he will be giving a talk anyway. So he is not here, so we cannot ask him now.
Have the similar problem in geometry.
Right.
Actually,
Okay.
cop and robber work in geometric plane, not in the graph plane in reality.
Okay. So next is, yes. So outcome is very easy. We have to collaborate, get some papers, and preferably the papers. So I think the goal of the giving this funding is to get some works done with both contributions from French and Indian side. So that will be quite important. So in this duration, we will try to start something which we can continue over Skype and probably have a finished work by the end of the project. So this is a 3-year project. So for each visit, we have to submit a report. And so please, if you do something, please report to me during this time so that I can list them down. And I will need some help from maybe Dibbayan and Shom the Bodhayan also for the visibility part. I have explained to you already, right? Okay, so let's start. So that was the technical details, some overview. So we are on the same page. Let's start with our first talk, which is again me. So I'll just change the slides. আমার স্লাইড কোথায় রেখেছেন স্লাইড আরেকটা আই গট ইট ডাউনলোডেড উনি জানেন আরেকটা স্লাইড আছে না দুটো ডাউনলোড করে হ্যাঁ Okay, so I will have to erase this. I will use the board at some point of time. Okay.
Hold the board in one hand.
Right.
Okay, the confusion has to be removed one thing.
Yes.
Arcane Beta University and then Arcane Very, I hope there is no confusion.
Arcane View or Arcane Very? Yeah, the name changed. Now it is again Arcane View, is it? No. Okay.
One way.
Arcane View, Arcane Very. Right. Right. So this is correct, right?
Correct.
Okay. Thanks. And well, so if you want to know about graph homomorphism, I think you have to read this book, and it's a yeah, right. And well, I cannot explain this whole book in the slide. So what I thought, I will pick one topic which I like and probably give an overview of that or tell you the story about it. And our work actually starts where the book ends, because we are speaking not about homomorphism of simple graphs. We are speaking about homomorphism of colored mixed graphs or oriented graphs and these things. There are small mentions in the book that those can be done. Now, what is homomorphism? So, well, so you have a graph. Now, we all know what is coloring, probably, but there are some first years also. Right? So, a coloring is you take a graph and you color the vertices in such a way that the adjacent vertices are colored differently. This is the classical color. Now, homomorphism, in homomorphism you need two graphs. Okay. So, you have this big graph and a smaller graph. Now, you define a function f which is a vertex mapping. So, the function is from the vertex set of the first graph, which is on top, to the second graph. And the way I have defined the function is with colors. So, that means on the top graph, all the vertices colored with red. So, all the vertices colored with red, they gets mapped to the red vertex in the second graph, in the smaller graph. And all the vertices colored with blue gets mapped to the blue vertex in the second graph. This is the mapping. It's just a fancy way of defining a function. Now, the only condition is if there is an edge in the first graph, uv, then their image fu and fv, there will be an edge between them in the second graph. Okay? And you see here what I have done by defining the mapping in such a way, it actually gave a two coloring of the first graph, which is a bipartite graph, so it's not surprising that it will get a two coloring, but it got a two coloring. And you know that all these colors, if you put them together, they will be an independent set, and all the blue colors, if you put them together, they will be an independent set, meaning no edges between them, right? And all the edges are in between. So, it's kind of that picture in a small version. Small version of that picture is here. So, in some way you can put this big graph and put it in a small graph. So, it has a homomorphic image of a small graph. Now, there are many properties which does not change if you have a homomorphism. So, those are called homomorphic invariant properties. So, for those properties, if you do not work on the big graph and instead work on the small graph, it may be easier for you. I don't know, I mean computationally, or even if you are working in theoretical things, and it may be easier for you. So, that's the, for me that is kind of a big motivation for studying homomorphism or trying to find homomorphism of graphs. Now, the chromatic number, as I told you before the definition of coloring, The definition of chromatic number is the least number of colors you use to color a graph. But using the definition of homomorphism, I can give an equivalent definition of chromatic number. So what is it? It says that the minimum number of vertices in H such that G admits a homomorphism to H. So in this slide, you see, you cannot think of a smaller graph than this where the first graph will admit a homomorphism to. And the chromatic number of the first graph, as it is a bipartite graph, no odd cycles, it is 2. Yes, please.
So does UV have to be an edge if V is an edge?
Yes.
No.
Oh,
the other
is no. Then it will be isomorphism.
Right. Okay. So if
Right.
graph on n vertices is homomorphic to the clique on n vertices, right?
Right. But you are looking for the smallest image. That is one image, but you are looking for a smallest image. But it can go to a bigger graph also, you know, right? Now in chromatic number, we are only focusing on the smallest thing that it can go to. But in general, in homomorphism, it will be very important that what is the structure of this target graph. It can be a sparse graph. That means your original graph has some sparsity in it, things like this. For example, if you say that the target graph does not have any triangle, then the original graph cannot have any triangle also. The first graph cannot have any triangle also. So things like this. And now we have a homomorphism version of the definition of chromatic number, and like readily associated parameter is clique number and clique. So I can define clique by saying clique are those graphs whose chromatic number is equal to its cardinality. Okay. So some people, actually it's more usual to define clique as a set of vertices, but here I have taken a bit of liberty and called it a graph, because we will do something similar later on in a general setting. Now, and the clique number is the maximum. So here cliques will only be complete graphs, as we know from before, but the biggest clique sitting inside a graph is its clique number. Okay. So it is a maximizing problem. But you see, as I have defined chromatic number with homomorphism, clique number with chromatic number, and so everything is coming from the homomorphism thing. So this is the last slide of my undirected graph homomorphism talk, but for this I need the board. Well, there are 3 slides maybe, all in the same line. Let's see. So here there are many things, of course. So first let's focus on that 4CT. What do I mean by 4CT? So 4CT is the famous 4-color theorem, which says any planar graph is 4-colorable. So if you give me 4 colors and if you give me a planar graph, it is possible, I'm not saying I can, but it is possible to color that graph with 4 colors. Okay? So planar graphs are graphs which can be drawn on a plane without the edges crossing, except maybe on the vertices. Now, but this is not the version I want. The version I want is, so what are planar graphs? Planar graphs are K5 and K33 minor free graphs. Okay. So this is a characterization. So let us see what is minor. So minor is you take a graph and you can delete vertices, you can delete edges, and you can contract edges, meaning if you take an edge uv, just put them together, make them a new vertex, and the neighborhood of u and the neighborhood of v, their union will become the neighborhood of the new vertex. Okay? So this way you can contract a graph. And everything here, every graph you can obtain by doing these three operations from G is a minor of G. Okay? So these are actually standard things. You can find it in any books. Okay? Now we know that K5, if a graph doesn't have a complete graph on 5 vertices as a minor, and neither has a complete bipartite graph, 3-3 bipartite graph as a minor, then it is a planar graph. Now it says that planar graph is 4 colorable. Fine, I want to change this 4 colorable notion as well. So as we have defined it with homomorphism, if it is 4 colorable, then this G must admit homomorphism to K4, right? That is exactly what it means by 4 colorable. Okay. Now, long before the 4 color theorem was proved, it was noticed that this K33 part is not really important for this theorem to hold. So what was proved even before the 4 color theorem was proved, that if the 4 color conjecture is true, then you can drop this K33 and still the graph will be 4 colorable. So a bigger class of graphs, just K5 minor free, I'll get rid of the bracket also. So you see, you take any K5 minor free graph, and that graph G will admit homomorphism to K4. It's an extension of the 4 color theorem, but due to the theorem that if 4 color conjecture is true, then this is true, we actually call it equivalent to the 4 color theorem. So we can write it instead of the classical statement, we can write this instead. Okay? So I'll again change it a little bit, well, completely. And so I'll say K5 minor free, this is a family of graphs, right? Everyone in this family, they admit homomorphism to K4. So we slowly changed the 4 color theorem, the classical statement, to say this. Okay? The arrow will always mean a homomorphism. So every element in this set admits a homomorphism to K4. Now you see there is this, even if you ask a kid, he will probably find some similarity here. So K5 and K4, 5 and 4. So let's go back a bit. How about K3 minor free? Maybe I should have written it somewhere. Okay. So let's see. So how about K4 minor free graphs? So do you know what these graphs are? These are series parallel graphs, 2 trees. Okay? And we know that 2 tree is 3 colorable, means it goes to K3. Okay? And now if I take K3 minor free graphs, these are basically cycles, okay? Cycle free graphs, trees and forests. So these are bipartite, so goes to K2. And of course, K2 minor free means just independent sets, no edges. K2 is an edge. So they go to K1. is this a rule? I mean, do we actually have kn plus 1 minor free this set of graphs going to kn? Do we have this? Well, the claim is that this is true. That's a claim, okay? And it's a very strong claim, and it's known as the Hadwiger's conjecture. So this is very interesting because already for n equals to 4, it's the 4-color theorem. So it's very, very difficult to prove. And for the generalization, we don't know. But the point is that here, using the notion of homomorphism, there is some way we can say something about it. Okay. So how long do I have? What was the, do you have the schedule? Okay, thank you. So, yeah, but I will start at 10 minutes late. Fine. So, are you going to do that? Are you planning to?
No, just.
So, if I do it, it's useful for you. Okay, then I'll definitely do it. So. Is it A? Oh, they meant this. Okay, fine. So where are the hats? Ah, I didn't put the hats. S and R. Okay. Ah, it's the other way around. Sorry, I'm not used to putting hats. Okay. S. S. Okay. No, it's Z. No. Yeah, this look weird for me. I'm not sure about these. But okay, so they have this theorem. Patrice Osonade-Mendis and Neshatril. So Neshatril, if you recall, is one of the authors of the book. What is the theorem? The theorem is quite complicated and it's a bit big. I tried to shorten it in my language. So let's see. So I keep getting confused. I will ask Eric to check. If there is a mistake, please tell me. So this is the shorthand notation of it, but I have to tell you what the meanings are. So first of all, M is, so here is where I get confused. Which is connected, M or H? So one of them is connected, right? So M is minor, so no point. So this is connected set of graphs. Yeah. Connected set of graphs. Okay. H is set of graphs. Okay. And forbidden M, I can take the blue one. Finite and connect. So the graph should be connected. Yeah, one of them.
Set of connected graphs.
Yeah, set of connected graphs. Don't take disconnected graphs. That's all. Yes?
So what is the highest
So I have put n, so 5. 5? Yeah. No, because I have put n equals to n plus 1 here, so 5. So K6 minor free graphs are 5 colorable. And for 7, 8, there are some partial results. That's all. And now, this thing means set of graphs with no minor from M. Okay. And this thing means set of graphs with no
Total internal reflection.
set of graphs with no homomorphism from ends of H. Okay. So this one is M minor free graphs, and that one is set of graphs where none of the elements of H gives a homomorphism to. Okay? And so the thing is, what they meant is, if you take the intersection of these two different kind of sets, so remember this is forb M and this is forb H, they mean different thing, right? This is forbidden minor and this is forbidden homomorphism. If you take the intersection of these two, then there exists something in the second one, some graph in the second one, to which everything in this intersection admits a homomorphism to. Okay? So it would be very nice if we could select this M and H in such a way that this intersection will give us this set, and this will give us maybe this element. Okay? Then the Hadwiger conjecture will have a proof. But we don't have that, but we have something close. So what do I mean by close? Let's take M equals to H equals to Kn. Okay? Let's take both the sets as Kn. So this is Kn plus 1 maybe. Yeah, just to tally with this. So Kn plus 1. So that means this set is what? Kn plus 1 minor free graphs, exactly this whole set. And what is the second set? Second set is some graph where Kn plus 1 does not give homomorphism to. So where does Kn plus 1, a complete graph, Kn plus 1 is giving homomorphism to G, what does it mean? That G has a clique of size Kn plus 1. But G doesn't have in this set. None of the G's have. So this should not happen. So all these G qualifies for the second set. So the intersection is exactly this set, because this is exactly this set and forbidden H is a bigger set. So the intersection is exactly what I want in the left hand side. In the right hand side, what do you have? We have some graphs here. This is a set of graphs which do not have Kn plus 1 inside them. So the clique number of those graphs is at most n. So I know that inside this set there is something which is a target for the whole thing. There is Kn also, but I don't know if Kn is my candidate or not. I know there is some candidate, but I don't know if Kn is my candidate or not. So if I can find my candidate and maybe optimize it, like find the candidate, there may be many candidates which satisfies this property, but if I can find the smallest such candidate then given, if we assume that the Hadwiger conjecture is true, then that smallest candidate must be Kn. There is no other option. So this is kind of a very close approximation to the Hadwiger conjecture, and this is a very difficult theorem. I have tried to mellow it down in explaining, but it is actually a 5-6 line, just the statement, and the proof is, I think, 5 papers, series of papers. So anyway, so this is probably according to Reza. I'm quoting Reza.
Give a method to find the image.
Yeah, but it says, it gives a guarantee that there is something. Yeah, it will be very big. It will not give you an optimal thing. Yeah, right. So this theorem, I'm quoting Reza, that is the closest known approximation to Hadwiger conjecture. Now, there are other links, like there is a edge coloring equivalent of the 4-color theorem due to Tate, which Seymour has generalized. And again, those equivalents can be captured with homomorphism, but it was seen in Reza's PhD thesis maybe. He noticed already that there is some cases. So the Seymour's conjecture had some odd cases and even cases. The odd cases could be captured using the language of homomorphism, of simple graphs, but even cases, it was not possible. So it was Eric, Reza, and Rolova's work, where they used sign graph to capture the even cases. And together, they were the Seymour's conjecture. So odd even is kind of here vague, because it depends on how you define the things, if you use n or n plus 1 kind of things. Now, so you see, now I have put Eric's topic in a big context, right? And okay, now, well, this could have been the main topic, but nothing much has been done here. You see, the homomorphism of undirected graph, it's a generalization of coloring. A lot has been done, a book has been written, but how generalized can you think of a graph? So we are working always on simple graphs, but how generalized can you think of a graph? How general can it be? So graphs are, you are just trying to capture some relation between a few objects. So you can think of just one directional things. The edges are, they have a direction. It's going from one way to other, but not coming back. So you put arcs. If you just put arcs and of one type, then they are oriented graphs. If you also put the second type of arcs, well, there can be different relation, right? Different kind of relations. You can go from here to there by train, cannot come back. You can go here to there by plane and cannot come back. This can be the traffic network, can be said this way. It's stupid, but it can be, hypothetically. So there can be 2 types of arc, one for trains, one for planes. And then there can be both-way traffics. So one type of edge, 2 type of edges. So different types of edges, different types of arcs. If that happens, they have called this 2-2 colored mixed graph. So the color is, type is given by color, but people get confused between coloring and the color of the edges, so I have called them types. But the name I didn't change. Oh, I changed. I made it just 2-2 mixed graphs. But then you can generalize mn mixed graphs. It has m types of arcs and n types of edges. Then, if you define homomorphism, you just want to preserve the specific adjacencies. So if uv is a edge or a arc of a type I, then FUFV should also be the edge or the arc, whatever the first thing was, of the same type. That's your homomorphism here. So you have, okay, I have an animation for this. Okay, so the homomorphism is the definition I told you already. And the chromatic number is, again, the same thing. I just mimic the previous thing for undirected graph. It's the minimum homomorphic image, the number of vertices in the homomorphic image. And, well, images are colors. And then, so you have chromatic number. click number I can define exactly in the same way, or clicks, H is a click if it has number of vertices equal to its mn chromatic number. Okay? And the biggest such thing sitting inside your graph, the cardinality of it is your click number. Okay? And then the notion of click number ramified in two ways, absolute click and relative click, because here the clicks can have non-adjacent vertices also, and you can never identify them because of the nature of the homomorphism. That will give us something called a relative click. I'm not going there. But now this is very generalized. These are the things under it which has been studied. So KH colored graph, you have different types of edges. And then you have sign graphs, which are basically plus minus edges, or 2H colored graphs. But then there is a switch operation. I think now we are calling it resigning, right? So some people call it switch, some people resigning. So resigning or switch operation on sign graphs, and that gives the theory that Eric will be talking about, or I gave you a glimpse of. Okay? It would be a nice task to extend the De Mendes and Neschettil theorem to sign graphs, but I don't know. And on the other side, if you just consider only the arcs, then you have oriented graphs, and there is this similar to switch operation. There is this push operation, and Sandeep Das will be speaking about it. And in the basic thing, you have these undirected graphs, which are just the base where we can build the theory on. So the book was mainly about homomorphism here, and a little bit of directed graphs also, wherever they could actually say it in the unified manner. But now our work is to go up there, okay, and prove some results there, but they seem quite difficult. So I'll just quote some results. So the first result is for planar graphs. If it is a mn mixed graph, then 5, so it's something like 5 into, so 2m plus n is a crucial parameter here. 2m is, so for each arc you have two directions, so that's why 2m, and n is for edges, so 2m plus n. For that parameter, it's 5 into 2m plus n to the power 4. This is the upper bound, and the lower bound is cubic. But we don't know how to improve any of them. That will be a quite difficult job, I guess. I didn't try very hard, but I think it will be quite difficult to do. And then the second result, it is not published yet, but it's a joint work with Obhiruk Lahiri, Kourag Mukherjee, Soumen Nandi, who is sitting here, and me. So we have kind of, so in this result, what we have done, we have attacked the tail of the problem. So given a girth, what is, if you increase the girth of the planar graphs, then at some point of time, it becomes equal. So the known result was with a 10 instead of 7 here, you have made it until 7. So it's improvement using discharging method. And some results with Sandeep Das and Nandi. Oh, I got your spelling wrong, sorry. And the first one. That is you, not on. So there is another Nandi whom you worked with. Okay. So it's for the family of, for the graphs with maximum degree capital D, and both the bounds are exponential. And if I put those numbers to 2, then there is maybe a slight improvement in some cases on your result. And the second one is for degeneracy. It's the exact, the result is like the exact expansion of CRS and their result. Now, yeah, for some click number also we have made something. So there is a typo. It will be P for planar graphs. So for outer planar graphs, we have settled what is the absolute and relative click number here. For planar graphs, the absolute clique number, there is a gap. This is almost the 3 times the lower bound. And I have asked Shushovan to prove that the lower bound is tight, but I don't know. He's doing a master thesis with me, so let's see. Anyway, so for oriented graph, this was a conjecture before that it will be 15. So the lower bound was tight there. We have proved that before with Eric and Oyon. And questions, well, the usual questions I can think of. For outer planar graphs with girth restriction, for planar graphs with girth restrictions, K-trees, what is the chromatic number or the other parameters? It's interesting to study the other parameters also, the clique numbers. And can you prove the dichotomy conjecture in this context? Like given a G, so Flohan maybe worked on such problems in some restricted case of this, right? So, yeah, complexity, yeah. And then for higher genus like toroidal graphs or projective plane or arbitrary genus, what can this problem mean? And if you have some answer, some restriction of this problem. Okay, so that's all. Thank you. Do you have? Okay, because we started late, so. Okay, then of course.